Bismillahirrahmanirrahim. Hello guys, I am Professor A. Ali and I welcome you all in class of complex analysis. In today's lecture we shall discuss about analytic functions and Cauchy Riemann equations. So firstly we will discuss what is analytic functions. A complex valued function is called analytic function if it is defined and differentiable at each point of a domain D. A complex valued function whose derivative exists at every point of a domain of the function, such function is called analytic function. Other names of analytic functions are regular and holomorphic functions. Next, if a function f of z is non-differentiable at a point x0, then x0 is called singular point or singularity of f of z in that domain. For example, if f of z is equal to z square, where z is a complex number, this function is an analytic function because for any value of a complex number z, you can check that the function is everywhere defined and everywhere differentiable in the complex domain. That's why this function is an analytic function. While the function f of z is equal to square root z minus iota, this function is not defined, not differentiable at z is equal to iota. So z is equal to iota is a here singular point of f of z. And further, this function is not this function is not an analytic function. Next I am going to move about Cauchy Riemann equations. So here we will state and prove the Cauchy Riemann equations. So here we will discuss about statement and proof of Cauchy Riemann equation. Cauchy Riemann equation in abbreviation form also called CR equations. This can be stated as the statement of the equations is this proof that the necessary and sufficient condition for a function w is equal to f of z, which can be defined as here u of xy plus iota v xy, to be an analytic function. If the following for partial derivative ux, that is the partial derivative of u with respect to x, partial derivative of u with respect to y, and partial derivative of v with respect to x, and partial derivative of y with respect to v with respect to y, these four partial derivatives exist and are continuous and satisfy the Cauchy Riemann equations at each point of the domain of f. The Cauchy Riemann equations are partial u over partial x is equal to partial v over partial y, and second equation is partial u over partial y is equal to minus partial v over partial x. So the criteria is this, that a function is called analytic function if it satisfies these equations, and if these equations are satisfied and these four partial derivatives exist, then conversely we can say that the function is an analytic function. So firstly we will discuss here necessary condition. Condition is necessary. Suppose that f of z is analytic, because here we suppose f of z is analytic, so by definition of our analytic function, the derivative of f exists at each point of domain. So this is our supposition, function is analytic. We will show that CR equations hold. So here w is equal to f of z, which is equal to u plus iota v. So by definition of f dash z, you know that what is the definition of the derivative of the function. Limit delta z approaches to 0, f of z plus delta z minus f of z over delta z. As here f of z is equal to u plus iota v, in this similar way here f of z plus delta z can be find as by increasing x with delta x and y by delta y. So then f of z plus delta z equal to u of x plus delta x comma y plus delta y plus iota v of x plus delta x comma y plus delta y, and by putting here z is equal to x plus iota y, this delta z will become this. Next, by separating real and imaginary part here, the u terms are here plus iota v terms are here, and by applying delta inside the brackets, this will become delta x plus iota delta y. And say this equation number 1. Next here, that is the important, for different directions in the plane, the limit of one should be the same. You know the concept of limit of functions of two variable. I explain here the concept of two variable function. As here delta z approaches to 0 and z is x plus iota y, this shows that delta x plus iota delta y approaches to 0. 0 mean that is the origin. You know that you can move to the origin by moving along different paths. For example, when you move along x-axis, you can reach at origin. In the similar way, when you will move along y-axis, then again you can reach at origin. Suppose you move along this curve, then again you can reach at origin. So there are many different ways to reach at origin. So suppose firstly we will move along x-axis to origin. So let us moving along x-axis. When you will move along x-axis, then delta y will be equal to 0. When delta y equal to 0 and delta x approaches to 1, then one take of the form. As our question number 1 is here, when you put here delta y equal to 0 here, and again here delta y equal to 0, and also in the denominator, the question number 1 will become ux plus delta x comma y minus uxy plus iota vx plus delta x comma y minus vxy over delta x, where limit delta x approaches to 0. By separating real and imaginary parts here, this is the first part, that is the real part, plus iota, this is the second part, that is the imaginary part. You know that the first part is the definition of the partial derivative of u with respect to x, because you can see here y is same, y coordinate is same in both terms, that is y is constant here, and x coordinate in both terms is different. Here x is increased by delta x, that is x plus delta x, and so you know what is the definition of partial derivative of u with respect to x. So this will become partial u over partial x plus iota, and this is the definition of partial v over partial x. Say this as a expression A. In the similar way, when you will move along y-axis, then in this case delta x will equal to 0 and delta y approaches to 0. So again the question number 1, that was this. So when you will put here delta x equal to 0, so delta x will be finished in this expression. So here delta x will be finished, this will become ux comma y plus delta y, and when you will put here delta x equal to 0, this term will become vx comma y plus delta y, and also in the denominator the term will be iota delta y only. So again by separating real and imaginary parts, this will become this is our because here delta x become a 0, this expression will become in the denominator iota delta y, and in second part of the last expression, when here delta x is equal to 0, this expression is iota delta y, cancelled out this iota with this iota, and again using the definition of a partial derivative, the first expression is equal to partial u over partial y, because here x is a constant and y is changed. Y is here increased by delta y, so this is the definition of partial u over partial y, and similarly here this is the definition of partial v over partial y, and here this expression is partial u over partial y with 1 over iota. This can be written as partial v over partial y, as we know that 1 over iota is equal to minus iota, so this will become partial v over partial y minus iota partial u over partial y. Say this as expression number b, because this is also equal to f dash z, and expression a is also equal to f dash z. So by equating a and b and separating real and imaginary parts, we have, by equating a and b and real and imaginary parts, we have partial u over partial x is equal to partial v over partial y, and partial v over partial x is equal to minus partial u over partial y. So this is the proof of the necessary condition. Next we will move to condition is sufficient. Now suppose that CR equations hold and we will show that f of z is analytic function, that is we will show that f dash that exists here. As we know that the nominator of f dash z is f of z plus delta z minus f of z. So to show the sufficient condition, firstly we will consider the nominator of the expression f of z plus delta z minus f of z, which can be written as, because f of z is equal to u plus iota v, and f of z plus delta z can be written as by increasing x with delta x and y with delta y. So the first bracket is the value of f of z plus delta z, and second is the value of f of z. Next I am going to add and subtract these two terms. That the first term is ux plus delta x comma y, and second is vx comma y plus delta y. So by adding and subtracting these two terms here in such a way, the first term of the bracket is ux plus delta x comma y plus delta y. With this term we subtract ux plus delta x comma y, and by adding this same term with second value of u, that is uxy, and again by taking here common iota from the imaginary parts and write these two terms as, the first term is of imaginary part is vx plus delta x comma y plus delta y minus v of x comma y plus delta y, and by adding again this term here with term vxy minus vxy. Second and the last, say this expression equal to 2, and here there are the 4 brackets in our expression number 2. The values of these brackets can be calculated by a trick which I am going to share here. Here the difference ux plus delta x comma y plus delta y minus ux plus delta x comma y equal to delta y partial u or partial y plus epsilon 1 delta y. How is this equal? I am sharing here a trick. You can see that here the coordinates, x coordinate in both terms, that is x plus delta x and x plus delta x, these coordinates are same, whereas the y coordinate is different. Here the in first term y coordinate is y plus delta y, and here is y. What is the change in the coordinates of y? You can see that here coordinate is y plus delta y and this is y. It means y is changing with delta y. First is y plus delta y, and in the second u, y coordinate is y. Both coordinate is changed by delta y. So writing here delta y and multiply it with, because our function is u here, so this can be written as partial u or partial y plus epsilon 1 is here error, something is extra here, so called it epsilon 1, that is into delta y. And again using this trick in the second expression, you can notice that here y is constant, y is not changed, and x is changed by delta x. Here in the first coordinate x is x plus delta x, and in the second u x coordinate is x. So the difference between both coordinates of x is delta x. So write here delta x and partial u or partial x plus epsilon 2 into delta x. Again for the third expression, you can notice that here y coordinate is same, and the x coordinate is changed by delta x. Here the x coordinate is x, and here x coordinate is x plus delta x. So writing here delta x, now our function is v, so write here partial v over partial x plus epsilon 1 dash delta x. And same by using same concept, the last expression can be written as delta y partial v over partial y plus epsilon 2 dash delta y. By putting all these expression in equation number 2, we obtain, question number 2 becomes, the left side of question number 2, that number 2 is f of z plus delta z minus f of z, and the right side becomes delta y partial u over partial y plus epsilon 1 delta y, by putting all the expressions that I have discussed here. Next, in these 4 brackets I am going to use CR equations because we suppose that the CR equation hold. CR equation was partial u over partial x is equal to partial v over partial y, and partial u over partial y is equal to minus partial v over partial x. Here we will use a partial this. Here we will use this CR equation in such a way. We convert the last equation in such a way that only partial derivative with respect to x should appear in equations. That is, here we will use partial u over partial y equal to minus partial v over partial x, and in place of partial v over partial y, we will write here partial u over partial x. So these four brackets will become here. The first bracket is by using using the CR equations, f of z plus delta z minus f of z is equal to minus delta y partial v over partial x plus epsilon 1 delta y. Second bracket is partial u over partial x plus epsilon 2 delta x, and this is the imaginary parts. Next, by combining all the terms of like terms that involving partial u over partial x. So the term that involve here partial u over partial x, this is the delta x into partial u over partial x, and again here partial u over partial x is present. So by taking partial u over partial x in from these two terms, and similarly by taking common partial v over partial x in this term and in this term, we have. So by taking partial u over partial x, we have delta x plus iota delta y, and from partial v over partial x we have delta x plus iota delta y, and all the remaining terms are here. From these two terms, by taking delta x, this will become this, and by taking delta y we have this. Say these two brackets iota plus epsilon 2 plus iota epsilon 1 dash, this is a complex number, say this is equal to delta 1, and this is again a complex number, say this is equal to delta 2. Also by taking these two brackets are same in first two terms, by taking delta x plus iota delta y common from these two terms, we have partial u over partial x plus iota partial v over partial x into delta x plus iota delta y, and these last two terms will become delta x into delta 1 delta y into delta 2. After this, by dividing both sides with by this term delta x plus iota delta y, we have f of z plus delta z minus f of z delta over delta x plus iota delta y in equal to partial u over partial x plus iota partial v over partial x plus delta 1 into delta x plus delta y into delta 2 divided by delta x plus iota delta y. Next, by taking a modulus on both sides, we have, and by subtracting this bracket from both sides, we have this equal to delta 1 into delta x plus delta 2 into delta y delta x plus iota delta y. Say this expression equal to 3. Firstly, we will solve right side of the expression 3 here. So here for this expression, I will use here two properties. Firstly, by separating modulus of numerator and denominator, and secondly by using triangular inequality of the complex number. This expression is less than equal to delta 1 into delta x, because here delta 1 and delta 2 are complex number which are independent from x and y. So we will take only modulus on that delta that involve x and y. So this will become delta 1 into delta x over the modulus of the denominator can be written as square root of real part plus square of imaginary parts. Next and the last important thing is that here we know that if z is equal to x plus iota y, and suppose here for clearance, suppose x and y both are positive, then we notice that z modulus is always positive here. You can notice that if x and y both are positive, then real part divided by modulus of z is always less than 1. For example, if our z is equal to 3 plus 4 iota, here z modulus equal to 5, then the quotient 3 over 5 is always less than 1, and similarly when we divide imaginary part by the modulus, this is always also equal to always less than 1. So here x over modulus of z is always less than 1, and similarly when we divide imaginary part y with modulus of z, this is also less than 1. So here this expression delta x modulus over delta z, this expression is less than 1, and the similar here delta y over delta z is always less than 1. And when we multiply delta 1 and delta 2 by the numbers which are less than 1, this expression will become only delta 1 plus delta 2. Say this sum equal to epsilon. Putting the value of this expression that is less than epsilon in 3, we have this is less than epsilon. What this show? This is the definition of differentiability. So that can be written as limit delta z approaches to 0 f of z plus delta z minus f of z equal over delta z, which is equal to the second number of the modulus, that is partial u over partial x plus iota partial v over partial x. This shows that here this is the value of f dash z. So f of dash z is equal to this number. This shows that the derivative of the function exists because the right side of this number is a complex number. So derivative of f dash z is equal to some complex number, shows that derivative exists. And this number can also be written as, by using CR equation, partial u over partial x is equal to partial v over partial y, and partial v over partial x is equal to minus partial u over partial y. Hence this shows that the derivative of the function exists. I hope this video will be helpful for you.